Today, we have Dr. Keith Eshleman is a professor at the University of Maryland Center for Environmental Science and is based at the Appalachian Laboratory in Frostburg, Maryland. Dr. Eshleman's research interests are in the areas of watershed and wetland hydrology, groundwater surface water interactions, biochemical processes in upland and wetland ecosystems, water quality modeling, and ecosystem responses due to natural disturbances, energy development, and land use change. Dr. Eshelman's field-oriented research program has broadly focused on man's impacts on the hydrologic cycle, specifically on examination of the hydrologic effects of acid deposition, forest disturbances, surface mining, shale gas development, urban stormwater management, and peatland drainage and restoration. And again, today, Dr. Eshelman's going to be talking about assessing the effectiveness of green stormwater infrastructure for addressing stormwater management goals at the watershed scale. I want to thank Dr. Eshelman for coming on out. He's actually done a really amazing webinar for us last year, and I'll be able to link that. You can find that in our YouTube channel as well if you go there later. So with that, I'm going to go ahead and stop sharing and hand it over to Keith.
And you should see the presentation.
Yes, there it is. We got it.
Okay, beautiful. Thank you, and welcome, and good afternoon, everybody. I think I can skip the first slide here because Missy did a nice job of summarizing what it is I'm going to be talking about. But the main topic here, of course, is green stormwater infrastructure and our field study to try to address the effects of this here in Maryland. So I want to just start by saying, summarizing what I talked about last year at a CSN webinar, and that was our work with highway bioswales. And in that study, we did replicated paired mini catchments to quantify differences in hydrologic pathways and the relative effectiveness of different stormwater treatments, looking at bioswales and grass swales. And what we found was consistently high reductions in overland flow from the bioswales, but runoff volume and peak runoff reduction were very inconsistent. We did find that greater abstraction and detention of highway stormwater runoff was not consistently achieved with the design, and the major weakness appeared to be a hyper-efficient under-drain system. The good news was that the bioswales were able to reduce orthophosphate concentrations by 37 to 86% relative to the grass swales, but the reductions in nitrogen and TSS were not observed. In fact, nitrogen concentrations and loads actually increased relative to the grass swales. And that led me to think that maybe bioretention, in fact, is a misnomer, that there may not be any bio to the bioretention. And just quickly, one of the things that we found was that these things were consistently undersized and underdesigned. They were designed to abstract 1-inch event rainfall amounts. But what we found when we looked at all the data was that less than 1-inch rainfall events are just sort of a small potato in terms of their contribution to storm flow runoff over the course of an entire year. Event rainfall events greater than an inch are entirely dominant, and that was across the board at all the sites that we looked at. So this kind of inspired us then to think about if we're not able to see bioretention at the practice scale, what about just sort of scaling up and looking at the watershed scale to see whether we could come up with some detection of the impacts of these things? So we're going to be working then here with a paired watershed study, went on for 5.5 years, beginning in the spring of 2019, just as COVID was getting underway, and ending late last year in 2025. And what we hypothesized was that, and this is part based on the swales work, we should see lower storm flow runoff, higher base flow runoff, lower runoff peaks, storm runoff ratios, reduced overland flow, more attenuated unit hydrographs, and lower event mean concentrations of nitrogen and phosphorus. So we set this project up out in the Maryland Piedmont, out here in north central Howard County. If you know where this is Interstate 70. You see traversing both watersheds. They're contiguous. PLBR is the developed watershed, which was developed back in the 1970s and 80s. The stormwater management there is conventional or gray stormwater management. It's about 2.2 square kilometers in area, and the impervious surface is about 19%. And then the developing watershed, if you want to think of it this way, the treatment watershed is being developed using green stormwater infrastructure. This is an unnamed tributary to the Little Patuxent River, or UTLP. The area is 0.8 square kilometers, and the impervious surface went from 12 to 16% over the course of the 5.5-year study. On the map here, you see Delta and Kappa. Those are the locations of our tipping bucket rain gauges, and the black dots are UTLP and PLBR are our stormwater monitoring stations. So just quickly, the common monitoring equipment at both sites. We installed stilling wells with intake pipes to the stream and an instrument shelter that housed a Unidata digital water level recorder. We had non-recording staff gauge. We used an in situ Aquatrol 500 to make 5-minute measurements of temperature, conductivity, water level, and turbidity, and had a tube that transmitted the data to our project website. We used programmable sequential stormwater samplers, these sigmas, if you will, to collect samples during stormwater events that we would then analyze in our laboratory. And we had, as I said, 2 unheated tipping bucket rain gauges at the locations I showed earlier. Okay, so long before we set on the scene, this is May 2015 imagery for the UTLP watershed. This is what we call the pre-development phase. And you see, as anybody that works when suburbanizing watersheds knows, there's really no pre-development phase. It's kind of arbitrary. And you see, even in 2015, there was extensive residential development here on the north side of Interstate 70. This development went in the early 2000s and 2010s. But you see, even below and south of Interstate 70, there was some golf over here in the western part of the basin. And then the red triangle here, of course, is our monitoring station that at that time wasn't in existence, but we found that the impervious surface area here was 11.7%. This is what the early development phase is. This is going to be our calibration period for the Bakke study when we showed up on the scene in the spring of 2020. And you see what it looks like here. I've outlined where the disturbed area is, which was about 12.7% of the watershed, about 25 acres. And you see there was already extensive development underway. Some roads had already been added. There's actually some homes that have already been put in here. But most of this area of development is considered disturbed and not impervious surface. But this is our calibration period. So just kind of keep that in mind. And by the way, that started in April of 2020 and went through March of 2021. This is what we looked like then in the middle of our late development phase, which ran from April of 21 into September of 2023. You see much of the development down here along the catchment divide in the southwest corner has been completed. The GSI there is fully operational, but there's still this central lobe that development is ongoing. One building completed, but the other 3 still under construction. So during this phase, of course, this is where we went from a disturbed area of about 12.5% down to 0, but the impervious surface went all the way up to about 16.1%. And then finally, this is what we consider the post-development phase from about September 23, 2 full water years, October 23 rather through September of 25, 2 full water years, 16.1%. And you see now everything is fully operational. The development is, at least this phase, for these phases of development has been completed. Okay, so let's talk about the GSI practices that were part of this development. There are really two main kinds. One is the use of dry wells, these M5 in the Maryland Stormwater ESD manual to capture roof runoff, and there were about 50 of those, and I just pulled a schematic here from the development plans. So we have that for roof runoff, and then we have 22 bioretention and micro bioretention cells that are used to capture runoff from paved surfaces. And just a couple words about these. There's some really nice features, and I've kind of shown one feature here in my pink shading, and that is this stone sump at the base of the bioswale. And this provides a nice storage for water that is percolated all the way down to the base of the cell. And the second feature here is the fact that the underdrain pipe is not situated at the base of the stone sump. Rather, it's in the middle, that allows for the formation of a temporary saturated zone that can then aid in the absorption of water, or the recharge of water through the adjacent media surrounding the bioretentions. And this, again, I didn't really say this, but the bioswales, again, were designed to capture 1-inch rainstorms. But these bioretentions, by virtue of the very deep biosoil media, were actually designed to capture 1.8 to 2.6-inch rainstorm events. Okay, so this is kind of just showing here, I guess, the good, the bad, and the ugly of suburban development in Maryland, and I suppose elsewhere. On the upper left, we see the super silt fences used to as the main E&S control. That, of course, there's some sediment traps also situated about the disturbed area. In the upper center, you see a case where the forest crew, I think, got a little out ahead of their skis and actually cleared areas that were beyond the line of disturbance here, the limit of disturbance, which is an issue. And then you see, notwithstanding the E&S controls there on the right, you see that this tributary stream still looked like chocolate milk during this early development phase, particularly. Really, not much can be done about that, I suppose. But I felt like, in fairness, again, I'm not judging the quality here of the development, but I think, just in honesty, I think we all realize that these are imperfect controls on erosion and sedimentation. And then down at the bottom, you see some of the bioswale or bioretentions, rather. The one in the bottom center has not yet been fully planted, and the one in the lower right, of course, absolutely is. Okay, this is an awesome data set. If I have to say so myself, 5.5 years of just really wonderful data. If I'd be 10 years younger, I would be challenged to actually get through all this and publish all this information before I retire. But let me give you the highlights so you know what I'm dealing with. We have rating curves for 2 sites over 3 to 4 cycles of discharge, including gauging during those flash floods that I mentioned. We have complete 5-minute gauge height and flow records, plus hourly rainfall data from 2 stations. NexRad level 3 data were used to estimate gauge adjusted aerial rainfall for more than 200 events and to identify outlier events. We did monthly base flow sampling at both sites. Over 200 storm flow producing events were characterized, including more than 50 with intensive water quality sampling. And this also includes quite a few extreme events, rainfall events, including a 20-year, a 7.5-year, and a 5-year event based on 1-hour rainfall. As I said, we have the 5-minute in situ data, conductivity, turbidity, and so on. We did chemical hydrograph separations using the conductivity mass balance for more than 150 separate events. Almost 2,000 streamwater samples were analyzed for 17 different constituents using standard analytical methods. And then something I can't talk about today, but I think I've already talked about this in another talk, was E. coli sampling and analysis during the post phase. Okay, just some of the highlights of the gauging work. These are our rating curves on the left. At Plumtree, these are great. I mean, we have a lot of stability here, but as with when any time you're using natural controls, there is some sedimentation and erosion, scouring, if you will, around the control that we have to deal with. We dealt with that at Plumtree Branch, shown there in the upper left. Down at the lower left, this is the UTLP curve. And one of the things we dealt with here in the very first year was a complete washout of our local control, shown there in the lower part of the blue curve. And you see we had to come in and actually add in the red points there to deal with this shifted curve after we rebuild our local control as best we could. So this makes a huge difference. If we hadn't captured this, sort of all bets would have been off in terms of our ability to characterize the runoff regime for this particular watershed. And then when we look at annual runoff over the 5.5-year study for the early, late, and post periods, here I've compared it against data from 5 nearby watersheds gauged by USGS. The Plumtree data agree very well with the neighboring watersheds that are all much larger, by the way. USGS gauges are much larger streams. Agrees very well, but you see there that the UTLP runoff is lower in all of those periods. So it's consistently lower. And as I said, I guess I didn't say this, that these highest discharge measurements were exceeded only 0.05% of the time owing to our gauging during these flash floods. Okay, two-component hydrograph separation. I'm not going to get into all the mathematics here, even though it's almost trivial. This is literally 7th grade algebra to solve these two equations, the water balance equation and the tracer mass balance equation. Suffices to say here that we used conductivity as our tracer, natural conductivity. And what we found in almost all the events, not quite all of them, was that each event produced a dramatic dilution in the base flow conductivity, going from, in this example for Plumtree, it started at 570. You see it was very stable, and then it dropped down dramatically during this runoff event, headed toward what we think the new water is probably like, which is close to 0. And then you see on the recession limb, the conductivity sort of rebounded, heading back toward its initial value. And of course, we can solve these equations by substitution because we have 5-minute conductivity data, and actually then draw the old water discharge hydrograph. And of course, the new water hydrograph would just be the difference between the total discharge and the old water discharge, shown here in the lower left panel, just as an example. So again, with the exception of winter events where we had road salting, where conductivity rose during these events, we found it's an excellent hydrologic tracer. We assumed conservative behavior. We saw consistent dilution. And by the way, the results were almost totally insensitive to the choice of this new water conductivity. We assumed 0, but it really doesn't matter if it's 5 or 10 or 20. The results are almost, like I said, totally insensitive. So there's that. But one of the problems with this is, of course, you have to do this on an event-by-event basis. So this became a rather tedious problem, if you will. And what I really wanted was a way of using a continuous hydrograph separation tool. And that's when we happened upon the recursive digital filter method of Eckert, 2004. You can find a tool online that does this very nicely at sephydro.hydrotools.tech, shown there at the link at the bottom. And basically what this is another 2-parameter RDF that separates the hydrograph into 2 components. And here they're direct runoff and base flow. There's a linear reservoir assumption that the base flow decays exponentially. So we have to come up with a recession constant, KB, which we can estimate independently from field data. But the second parameter, BFI max, this base flow, this maximum value of the base flow index, is unknown. So here we married the conductivity mass balance and the recursive digital filter by assuming that the old water from the conductivity mass balance is the same as base flow, and the new water is the same as the direct runoff. And then we can take all that data from those hundreds of storms that we separated and estimate BFI max by trial and error using those data sets. And this worked beautifully. You see for both PLBR and UTLP. For PLBR, we were able to get a coefficient here, an X coefficient of almost exactly 1. The R squared is 0.95. And by the way, this is stable over time. And at UTLP, surprisingly, we found it's also stable over time, although we separated these hydrographs into the 3 different development periods, early, late, and post. But we found the same value of BFI max of 0.75. So BFI max at PLBR was 0.675. We got a value of 0.75 for UTLP. All right, so let me say something about the BACI modeling approach that we're going to be using here. So I didn't really want to get into this, but I feel like I need to. Not everybody's going to be familiar with this, but the basic idea of BACI is a before-after control impact design. So they're basically, you're going to come out and find, at least as applies to watersheds, you're normally going to pick a pair of watersheds here, watershed A and watershed B. They don't have to be the same exact size. They don't have to necessarily be contiguous, but it usually helps if they're in the same general vicinity and they maybe are the same land use. But what you do is go out and select and instrument the watersheds, collect the calibration data for both watersheds using the same methodology, then develop BACI models. That is, models that relate some parameter that's measured at both watershed B versus watershed A for the calibration phase. Now, by the way, some people think that the BACI design is a panacea, but it turns out right off the bat that you can see that it isn't. So you might go out, for example, and select an instrument 2 watersheds, go and put in a tremendous amount of instrumentation, collect a lot of data. Well, what happens if you can't develop the BACI model? You've wasted an awful lot of effort and time and energy, and you really have nothing to show for it. So this is one of the real limitations of this. You're not guaranteed a result. Turns out in our example here, we're going to be able to get some good results. But then in the treatment phase, what do? Obviously, you perform the treatment. So say you go in and clear cut the watershed or you suburbanize it, collect comparable data, and apply the BACI models to make predictions for this watershed B that represents the treatment or the impact watershed. And then you're going to compare the predictions with the observations, and any differences are going to reflect treatment effects. And then you do the same thing for the post-treatment phase. Okay, so I'm not going to get into this, but except to say this is one of the most famous BACI watershed studies that was ever done at Hubbard Brook Experimental Forest in New Hampshire by Herb Warman, standing here very proudly by his concrete V-notched weir, and Gene Likens, very famous biogeochemist, that was the sort of the co-conspirator here. And of course, here what they did was went in and did this thing in the upper right, this deforestation practice. And then as shown here in the lower left, they made measurements of the pre-treatment monthly runoff from these watersheds and compared those with the post-treatment differences, did this using the BACI design, and were able to find very statistically significant differences and thus quantify the treatment effect. Now, I will say there are very few examples of this design being used in urbanized watersheds. So that's what we're going to do here. But before I do, I want to mention one other thing about BACI, and that is it's not essential that you have the same hydroclimatic regime throughout the entire BACI experiment. So here's data showing drought conditions for Howard County, Maryland, in which we did our study from 2020, the beginning of 2020, all the way to the end of 2025. And you see there was a lot of variability in drought across this region. So this could present a challenge were it not for the use of the BACI design. And in fact, this is exactly the problem we faced. Here's the early period that we're going to be looking at, where the period was very wet, almost no drought whatsoever. The late period sort of oscillating between a wet period early on and a very drought period toward the end, and then kind of a mixed bag of wet and drought in the post-development period. So this is real. This is what we're going to be trying to control for, if you will, using data from the PLBR, the Plumtree watershed. Okay, so let's just look quickly. This is data from the control from PLBR. These are our 6 rainfall runoff metrics that we're going to use. So we're going to be looking at event aerial rainfall, event runoff coefficient, peak event runoff, event direct runoff coefficient, and the event base flow coefficient. And what we see right off the bat, just for the control now, for the 3 periods, is 5 of these showed no significant differences in means using a t-test. Big sample sizes here, by the way, as you'll see. But we did see a difference, a statistically significant difference in event runoff coefficient. And we kind of scratched our head. That seems like an oddball, given that it looks like event runoff was actually maybe going up and event aerial rainfall was going down. Why would the runoff coefficient be lower in that early period? So we looked at the differences in rainfall distribution among the different storms we studied and the maximum rainfall intensity over this. And I have some hypotheses here, nothing firm. I do think it's interesting in the lower left there that in the early period, we seem to have a reduced proportion of these less than 1 centimeter per hour events compared to the other 2 periods. So perhaps that's what's going on. Just had more of these sort of modest events. We really don't know, and it's not critical that we have that, because we do have, again, in the BACI design, the ability to control for these differences among periods. Okay, so let's look at the BACI hydrologic models then. Here are 6 metrics that I talked about. And the good news is, yay, we were able to find statistically significant BACI models based on data from the early period. N equals 34 here. Everything looks good to go. I would point out at the lower left here that for peak runoff, in order to deal with the assumptions of linear regression, we did have to log transform the data. So everything, and that worked beautifully, by the way, you see there. And then from then on out, of course, we're going to have to back transform to get to do our statistical comparisons. Okay, so this table then summarizes our application of the BACI models to make predictions, predicted mean values for the late phase and the post phase periods. And again, you see the sample sizes here are pretty huge. So what we see here is PLBR versus UTLP, observed versus observed. And then for the post phase, you see a comparison of the observed and predicted values based on the BACI model. So what did we find? We found, again, aerial rainfall. There was no significant difference from period to period, nor was there a difference between the observed and predicted values for the treatment watershed. But when we look at 4 important metrics here, runoff coefficient, peak runoff, and direct runoff coefficient, we found statistically significant differences. And we found that the percent change, if you will, or the treatment effect, was almost the same percentage in each case, about 30%. So about a 30% reduction, if you will, in event runoff, runoff coefficient, peak runoff, and the direct runoff coefficient for the post phase. Okay, so it's about uniform. And then, of course, we saw, because the direct runoff coefficient and the base flow coefficient have to add up to 1, we saw about a 50% increase in the base flow coefficient. This is the treatment effect, right, of the GSI as part of this development. Okay, so let me explain what this is telling me, and I want to make a physical interpretation of this for you. So I think the easiest way to think about this is to put a conceptual hydrograph on the board here to represent the predicted event hydrograph for UTLP for the post period. And I'm just going to make this thing into an isosceles triangle for simplicity, because I can integrate this. It's trivial to integrate, and I think you can follow it most easily. So obviously Q sub P divided by A is the peak discharge divided by the watershed area. And I'm just going to set it to 1 arbitrarily. Doesn't really matter. And I'm going to set the time base here, the base of the isosceles triangle, equal to T, and also equal to 1 unit. So obviously the runoff, the stormwater runoff here, is going to be the area within the triangle. I'm going to denote that as R. And it's easy to show here because we know that the area of the isosceles triangle is 1/2 the base times the height, that for a QP divided by A over of 1, we would get runoff equal to 0.5, right? So the ratio here would be exactly equal to 2. Okay, so then let's go to the observed event hydrograph for UTLP. And remember what we said. We said there's about a 30% reduction in both runoff and peak runoff for that hydrograph, for the actual observed hydrograph for the post period. So that's going to look like the one I've drawn here. So the peak is now down to 0.7, and it's very easy to show that to get that runoff also equal to, or the runoff reduction also equal to 30%, that this thing has to have the same exact time base, namely the duration has to also be equal to 1. You can prove that to yourself very easily. So what we saw of a minus 30% mean treatment effect for both peak discharge and event runoff is a special case, okay? It's very easy to come up with cases where you see greater reductions in peak runoff per unit area for the same reduction in runoff, but those are only gotten by extending the duration of the hydrograph. Like, for example, if there's anybody here that's worked with storm routing or reservoir routing, that's what happens in storm routing or reservoir routing. We just get a redistribution of water across the hydrograph, okay? But that's not what we see here. We see the same 30% change, which means then that the GSI implementation has decreased event runoff by the same percentage, and that has to be by retention, essentially taking water out of the equation. Now, let's just make this ever so more complicated by then putting in the other thing that we found, namely the changes in direct runoff and base flow coefficients. And you remember for the prediction, we had 0.67 and 0.33 were our coefficients. So I've drawn those in, which means that we can then draw a base flow triangle hydrograph that goes up to 0.33. And of course, the area in between this one and the total would be the direct runoff. And then we can do the same thing here for the observed event hydrograph. But here, if you recall, the coefficients were 0.5, which means then you can see right off the bat that the base flow hydrograph, the runoff is going to actually be greater in terms of volume, and it's going to be greater in terms of relative contribution as well. So again, doing the math, the change in the base flow runoff would be about plus 6%. I don't know if that's statistically significant or not, but that's what we get. We get a little more base flow volume, and we've already seen that the coefficient itself goes up by 52%. And this means then that GSI implementation appears to be able to increase both the absolute and relative old water contributions to storm flow. So this is going to turn out to be kind of interesting as we move into the final topic I want to discuss, which is what did we find out with respect to water quality? Again, there's good news here in terms of BACI modeling. We found some statistically significant regression models for several constituents, including nitrate nitrogen, total dissolved nitrogen, and total dissolved phosphorus for base flow, for storm flow, event mean concentration, and for storm flow load. So these are nice models that we're then going to apply to see if we can ferret out or detect a treatment effect on UTLP. So this is going to be the most complicated slide of the day. Fortunately, there's no exam on this at the end, but let me just take a minute to share what we have here. Basically, let's not worry about the chemodynamic behavior. We could come back to that later were there time, but let's look at then what these three groups of bars are showing or columns are showing. We have then base flow concentrations. We have whether a model question mark, could we get a model that's statistically significant? N/S says no, check says yes. Late diff, did we see a treatment effect for the late period? And then post-diff, did we see a treatment effect for the post period? And then the same thing here for storm flow EMC and for the event load. So if we see a red check under these treatment effects, that's bad. That means we actually saw an increase in either concentration or load. Green is good. Green, we saw their treatment effect is actually a positive thing. We're seeing a reduction in either concentration or load. And the first thing you see is we've got a problem, Houston. We saw an awful lot of red checks are bad and relatively few green checks are good. Okay. And of course, we see quite a few non-significant. And we also see quite a few constituents like TSS there at the top, for which we could find no statistically significant model there for either the EMCs or the storm flow. And the same goes for things like total phosphorus and particulate phosphorus. So there's a lot here we lack, and this is going to take us another place. But let's just look quickly and see if we can learn something using the nitrate data. So let's again try to mix our nitrate here. So here's what the data told us for the prediction period. We're going to presume we're going to mix new and old water. And if the only thing we don't know here is something about the new water concentration. And it turns out if we do the math, we come up with about 0.65 milligrams per liter. So what does it tell us about then for the observed period? Again, we see the change in the direct runoff and base flow coefficients. We're going to plug in the 0.65, use the same old water concentration, and calculate what the storm water ought to look like. These are mean values now. And what we come up with is a value of 0.88. So we're saying that the model, as we've talked about, or the models, are predicting an actual increase from 0.8 to 0.88 milligrams per liter. Not a lot, about a 10% increase. And what did we actually see? We actually found the measured value was about 0.91. So that's pretty darn good agreement, which tells us then that the conceptual model is suggesting that GSI implementation can actually increase stormwater nitrate concentrations. But remember, since the area of this trapezoid is smaller by 30%, the event load of nitrate should change by minus 23%. So the load should go down, but the concentration is going up. So that seems counterintuitive, I know, but that's what the data and the model are telling us. So let's look if this is actually plausible. So here is our Bakke load model for nitrate based on the storms for the earlier period. Here is our nitrate event loads observed and predicted, and voila, the model is predicting for the late period a 22% or minus 22% treatment effect. So it looks like, boy, this looks like it's really promising. We're happy with this. This is green is good. But what else? Well, we see that that difference completely goes away in the post period. We see virtually the same value predicted for that period by the model. So this is telling us what? It's telling there may be a post-development stormwater source of nitrate nitrogen that we have not considered. So we could talk about that maybe in the discussion section if people are interested. So in conclusion then, I think it's fair to say that the Bakke design provided very strong evidence that the green stormwater infrastructure here has reduced storm flow volumes, direct runoff and peak runoff by similar proportions, i.e. by 30%, demonstrating it is possible to detect hydrologic change in watersheds with only modest land use change. You don't have to deforest the entire system to see the impact. The GSI at UTLP is a much better fit than the bioswale infrastructure, given Maryland's humid subtropical climate with fairly intense but infrequent rainstorms. And the reduction of each storm flow metric was of similar magnitude as the percent decrease in the total disturbed and impervious surface from the early phase of development. And what's the mechanism here? What can I say? Well, we think that the GSI and the hydrologic connections that it makes with the surrounding system are critical here, which enables local subsurface recharge and into those B and C soils, by the way, that surround the infrastructure and enhances the base flow regime. And it's also noteworthy here, something else I didn't talk about. These bioretention cells were intentionally placed such that they can discharge at outlets within the riparian buffered area. And this allows then for additional evapotranspirative demand to be fulfilled by that forested riparian area, which means we can get additional retention from a sort of runoff, run-on behavior, running off of the GSI back onto these riparian areas. In terms of water quality, we found no evidence of pollutant bioretention, as in the case of the bioswales. And in fact, we found evidence of greater pollution associated with base flow for some constituents like nitrate. Same deal as what we saw out at those highway bioswales, by the way. And we also found, unfortunately, there was an absence of Bakke storm flow models for several constituents like TSS and TP, like I mentioned. So we couldn't directly use the Bakke design to evaluate the efficacy of treatment for these constituents. So this has allowed us then to think about alternate modeling and approaches. And I'm going to leave you with this slide. We're going with LODEST, which is a model that I've worked with before, a USGS loading model, Runkle et al. 2004. And this really is showing some promise. I'm not going to get into the detail today. It's a whole other seminar. If you'd ever want to consider me bringing back maybe a year from now, I think we'll have way more on this to share. But this looks super promising, and maybe this is the way around the lack of the Bakke models. So in terms of acknowledgments, I thank the sponsors, the Bay Trust, for two projects, actually. Well, three if I include the bioswale work, DNR and SHA, a longtime sponsor of the bioswales. Howard County government was great. Mark and Caroline, thank you so much for getting us the permits to trespass on your land, set up instrumentation and so on, site development, the impervious surface data. And then, of course, the team here has been wonderful. 7 different people gave of their time and effort to help this thing through to the very end over a tough time, honestly, working through COVID, a field project that was 2 hours away, and so on. And then again, I shout out to my younger son Neil and my wife Liz, who I couldn't have done with. These were my field techs back during COVID, and again, without them, all bets would have been off. So that's it. So I think I can stop my share probably. And I see Missy, and I see I'm like right on schedule, which is scary.
Yeah.
And allow us time for any questions, I guess, that folks have. Thank you for your attention.
Yeah, thank you, Keith. Thank you so much. So I do have a question that came in a little bit earlier on. I didn't want to interrupt you, but from Fernando was asking, can you please clarify the old water and new water terms?
Yes. So the old water, new water is really thinking about hydrograph separation from the standpoint of a time-based separation. So old water would be assumed to have the chemical composition of water that was on the watershed prior to a particular storm flow event. So that would look like the base flow in the stream, for example, right? That's your old water. That was there. It doesn't matter if there's a storm flow event or not. Presumably that base flow composition would continue right on through the event. The new water then, again, is a chemical composition of the water that was deposited onto the landscape and or might have extracted some constituents from the land surface, but it's new in the sense it's new for that event. It's part of that particular event. So some people call it pre-event and event water would probably be a better term. Honestly, I like old and new, but each to his or her own there. But again, I hope you got the idea that I'm going to equate new water with direct runoff. There should be some correspondence between the two. The old water with the base flow composition of that event. I'm going to equate those two things to allow me to calibrate that recursive digital filter. Good question. Sorry about not clarifying better.
No, thanks for answering that. We also have a question from Thomas. He said this is a really interesting study. Thanks for sharing it. This study is for new GSI. Will you continue the study to see if there is any degradation over time? What is the GSI maintenance and who will be doing it?
What are you trying to do? Kill me? I'm 69 years old and devoted my life, 5.5 years of my life to this. Be realistic here, folks. No, I'm just kidding. This is a labor of love. Honestly, if you knew me, you'd know this is a labor of love. I'm pondering right here how I'm going to go on in retirement without being involved in this project. So this is where I do my outreach to the 89 participants and say, I have left quite a bit of the infrastructure in place. This ended the end of last September, right, with the end of the water year. I am still kind of, what's the word? I'm kind of monitoring. I'm still going out and downloading water level data. No more water quality sampling. We don't have the money for that. The projects are over. The sponsorship is resolved. I'm writing the final report. This is an outreach to say if anybody out there or people have an interest in using these watersheds for something from now on into perpetuity, either involving me in some capacity as a consultant or somebody or not at all, you're welcome to it. Now, you'd have to figure out with Howard County whether we can extend the right of entry and blah, blah, blah. But if people want to do it, I think it would be an awesome idea, really. And as I said before, remember, the developing watershed could flop over and be the developed watershed. And in fact, that's what's actually happened. Now, in the upper northwest part of the Plumtree watershed, a new development is going in there. I guess if you're in eastern Maryland anywhere, the undeveloped watersheds abhor a vacuum is what it seems like, right? It seems like development comes in almost regardless of what we do, right? So that watershed, our control or reference watershed, is in itself developing and has been developing over the last year. Whereas it looks like now at UTLP, that is stabilized at least for the moment. But you're absolutely right. I think more people have asked that question maybe than just the Fernando. If you please reach out to me, I don't have my email or my anything here, a phone. Ring me up, call me, talk to me. I'll help you. I'll do whatever. I'd love to see this go on in some capacity. Sorry about the long-winded answer. You can tell I'm excited about it. I was really almost praying that somebody would ask that question. Honestly. Great.
Excellent, excellent. I think, Keith, your passion for this is very evident, and I
I
appreciate
hope so. I
that.
really, it's genuine too. I mean, this is what I've given my life to, and I shouldn't say it like that. I've gotten a lot out of it, but I learn every time I go out there, and this is what makes this so worthwhile. Yeah.
A question kind of along the lines is Kyle was asking, is there any data to show how this would play out over a longer period of time or with older bioretention cells that have experienced clogging and or maintenance issues?
Yeah, I will say now, remember, the only experience I have directly is those highway bioswales, which we studied for 8 years, by the way. It's not like a slapdash, we got in and got out. That was a long study unto itself. And by the way, that overlapped with this. So that was really some work to do. And here's what I'll tell you. We did not see evidence of clogging at any of those highway bioretentions. So remember what we're doing. We're measuring both the water coming out as overland flow through the flume and water coming out of the under drains into those stormwater inlets. We did not see evidence of clogging. What we did see was evidence of folks tampering with the cleanouts where people came, there were capped. These were supposed to be watertight cleanouts. Those were opened up. Maybe they were used to clean out those, maybe State Highway, honestly, took a crew out and tried to clean out some of those under drain pipes. That's certainly possible. But we did not see evidence of clogging either in the water quality data or in the runoff data. Those things were as efficient at producing under drain runoff literally from the day we started studying, as far as we can tell. Now, I shouldn't say there's none, right? It's a detection issue. Could have there been some small clogging? Possibly, but honestly, it would be tough to tease it out.
Excellent. Okay. And I have two kind of design questions for you when it comes to, so Fernando asked, what do you know about how the GSI was constructed? Was it confirmed that it was built to design? And then Alexander actually asked something similar. So you mentioned a few good things about the design of the GSI and the development, i.e. sumps and placement. Are there any design weaknesses which you think contributed to the water quality performance or any design improvements that could be made?
Yeah, so let me answer the first part as best I can. I cannot. I did not do any independent validation that the GSI was constructed as per the plan in this development in what we were talking about today. Now, for the bioswales and those bioretention areas, we did exactly that. So we actually went out and actually cored down through the bioretentive soil to actually make a comparison of the depth of the biosoil media with the design specification. And we went out and actually measured the area, the surface area of those bioretentions to confirm, yes, in the case of those bioretentions, those bioswales, those were built again to specification. Did they have design weaknesses? Yes, I already talked about that. They're too small. They're probably not deep enough. That under drain pipe is at the base of that stone sump, so it doesn't provide for the formation of a transient saturated zone. Doesn't do any of that. I think that's a flaw. It did through not through bioretention, but we think through chemisorption, do a great job absorbing phosphate above and beyond what we saw in the grass swales, which weren't strong absorbers, it did not appear, of ortho P. So we saw some great stuff. Again, I'm talking bioswales now. I'm not talking the ones here at this. So I'm going to answer the second part of that. Well, what about this project? What are the design limitations? One design limitation may be, I'm not concluding it yet. It may be that we're not seeing the phosphate sorption that we saw at the high bioswales because we may not have the right media in these things. We haven't confirmed that the media, the planning mix, so to speak, that was used in these systems is commensurate with allowing for that sorption to actually take place. I'm assuming it's not. But again, I'd like to do my Lotus modeling. I'd like to look at a little more data, a little different way before I draw that firm conclusion. So it's more of a hypothesis. I'm just wondering if that is very if that's going to allow for that sorption to happen. I'll put it as a question. Sorry, I can't be more definitive, but we did not get, as I showed, we did not get many strong models for phosphorus. That's just, again, that gets back to what I said before. You can do a hell of a lot of work, go out there and get all this data for a year or two, and then it's like, well, what the heck do I make of it? I can't get a good model. So that may be it may be a case of that, honestly, which would be disappointing. But we're not perfect. As my aunt used to say, we haven't all died and gone to heaven yet. It's still a tough go.
All right. Lee actually had a comment here. In the early 2000s, you did a paired comparison for 1 year pre and year post installation of stream projects in subwatersheds of the Severn River. It was striking that 70% of all sediment loss occurred in 24-hour event with 4-inch plus rainfall. This suggests that spillover areas deserve much more attention.
Yeah, that could be. That doesn't surprise me at all. And I think probably you said that was for sediment, correct? That was for total suspended sediment. I think you might see something very similar to that, looking at total phosphorus and particulate phosphorus in particular. That would not shock me. That not shock me one bit. That may be what's going on. Although I don't think in the example here we're seeing spillover in terms of overland flow. I don't think we ever exceeded the capacity of the bioretentions in this particular example. So maybe unique to the stormwater infrastructure that was used in that study.
Okay, and we have a question from Nicole. It says, and I'm not sure if this is something that you can, comment on, but can you share your opinion on green roofs as a cost-effective GSI? Do you have an opinion on that?
No, honestly, I don't. I have no experience. It's, the only opinion I'd have would be formed on the basis of what I've read. And it's a mixed bag there. Honestly, I think there's a mixed bag. There may be some utility in terms of the hydrology side of the house. There may be some storage release function. So attenuation of peaks might be part of that story, but I'm not aware of having seen any water quality benefits. But it may be out there. So I shouldn't even comment, honestly.
Okay, and Roger had a question. I fight stream restorations and propose we use more GSI for MS4 credits. Do you think there's enough places to do that much GSI?
That's a great point. And, I often, we talk about this. I didn't have time, and I didn't have time to get into anything about the Plumtree watershed, the older development with the gray stormwater infrastructure. But there are several examples within that watershed as I drive around, just sort of looking at what's going on when I'm out there storm flow sampling. And I look and I say, oh, that would be a great place to do a retrofit, to actually do a bio cell and try to address some of the problems you see on the ground, right? I'm right there. It's raining. I can see literally the water flowing off of the road right into the stream. It'd be a great place for a bioretention cell. But it's hard to do, isn't it? Because of the limits of space and of ownership and all those kinds of things that come into play. So those people that are trying to do retrofitting, I mean, I think it's going to be a struggle. The beauty, if you will, of this study and of the design was that the developers, I guess, in their permitting, had to take lots that were what could otherwise have been developed and utilize those for GSI. They did that, and that's a whole different game when you start from the ground up. But when retrofitting is in, it's I think it's going to be an imperfect world, isn't it? It has to be. You're not going to be some places you're not going to be able to instrument or to effectuate a strategy. Other places you probably can. So you could probably just almost drive around and say, or maybe looking at aerial photography, and you could say, here's a place where we're conveying stormwater into a stream and it's going to be hazardous. We really need to ameliorate that impact. So let's look at what we can do on the ground. Yeah, it's tough. I appreciate that, and I think it's the same probably for you talked about reforestation, floodplain plantings and so forth. There it might be a little bit easier, honestly, because you don't maybe have the space requirements or the ownership issue.
Excellent. Well, we are just at time. Keith, I want
Beautiful.
to say thank you so much. This has been fantastic. As usual, you're an amazing presenter. We really appreciate you sharing the really important work that you've been doing. And if anybody is interested, again, Keith did do a webinar on his bioswale study as well. You can find that on our YouTube channel too. And if you have questions that come in, you can just email me. It's missy@chesapeakestormwater.org. Email me and I'll get you in touch with Keith, no problem. All right. So,
Or like I said, if there's that, and please think about this. If there's any way that you could offer your help in any way to keep this study going or to see it extended or branched out or whatever we want to call it, please get in contact with me. You can find me. I'm easy to find. I'm here in this little office about 50 hours a week, so I'm not going anywhere that I know of. All right, great.
right. Well, thank you, Keith, and thank you everybody for coming. All right.
Thank you all. You bet. Have a good day.
You too.
Bye bye.